Yep, okay. But do you have any good guess? Do you need 100 points? Do you need... How many do you need? You need 10 points? Do you need 20 points? Or do you need a lot? So where would you... At least, okay, so at the very least, it looks like you need to capture all the bottoms and all the top, right? At the very least. Okay? Right? So we can just count quickly. 1, 2, 3, 4, 5, 6, 7. Oh, I lost count. Many, right? Looks like we'll need at least a couple of 100 points to be able to capture the signals. Okay? And that's what we got from Shannon's sampling theorem. You have to sample twice as fast as the highest frequency of the signals. And in this case, it looks like the highest frequency is pretty high. It's wiggle a whole lot, right? So you at least have to keep up. Because if you measure here and then you measure here, then there's no way that you can tell what's going on in between, correct? You at least have to capture this and that and this and that and this and that to even have a shot. And even that is not enough. Typically, it has to be a little bit farther than that. Okay? So the question is, so that's the conventional Shannon sampling theorem. Okay? Now, I'm going to show you a relatively new field. Just being discovered within the last 4 or 5 years that actually revolutionized the sampling theorem. Okay? So this is what's going to happen. Here are my measurements. Here are my measurements in red. So I take about, you can count, maybe about 30. I take about 25, 30 measurements or so. And I claim that from those 25, 30 measurements, I can recover the blue curve perfectly. Okay? So there you go. That's the recover. That's the recover. Oh, I was running a pretty intensive optimization problem, you see. So there's many iterations here. There was a lot of computation involved, but at the end of the day, I come up with the red curve. And how close is the red curve comparing to the blue curve? It turns out that the red curve and the blue curve is exactly the same. Because if I hold the red curve and I plot the blue curves, it's right on top of each other, right? You cannot see the red one, right? So, and the mean square error is 0. The mean square error is 0. So in this case, we recover the blue curves perfectly from those red dots. We recover the blue curves perfectly from the red dots. Okay? Sounds like magic, right? So that's what compressed sensing is about. Okay? Now, why is it so is Shannon wrong, or so did we make a mistake in the Nyquist sampling theorem? It turns out that no. This is achievable because this signal is sparse. Okay? That example that I just showed you is achievable because the signal is sparse. Now, what exactly is, what do I mean by the signal is sparse? In frequency domain, if you take the FFT of that signal, it turns out that it only has 5 frequencies. It only consists of 5 frequencies. Okay? So we can describe this signal perfectly with how many parameters? How many parameters do I need to describe this signal perfectly? 5 is not enough. How many? 10. Why 10? The location and the magnitude. I need 10 numbers to describe that signal perfectly, right? The first 5 numbers I'm going to spend is the location of the significant frequency, correct? The second 5 numbers I'm going to spend to tell that this guy is here, this guy is here, this guy is here, this guy is here, and this guy is there. So I need 10 numbers. Okay? Now, how many red dots did I put there? More than 10, right? About 25, 30 or so. So a slight oversampling of the true number of parameters I need is enough for me to recover the signal. That's what compressed sensing is about. Okay? So let me remind you one more time that compressed sensing or perfect recovery of the blue curve is possible because the signal is sparse. Okay? Now, the magical things is that we don't know where those 5 guys are, and we don't know how high they are. I have no idea. The only information I have is that there are 5 guys in there. Okay? And those 5 guys are randomly picked. Okay? So this is one of the exercise that I want you to confirm in the afternoon when we do the optional lab session. Recreate this experiment. You randomly generate the cosine. You randomly give it the amplitude, and you recover and convince yourself that it's doable. Okay, by some simple optimization problems. Now, the next thing I want to show you. So forget this. Now, if I do the pseudo inverse, I get the one in yellow. So the pseudo inverse doesn't work in this case. Okay. Now let me show you another example. Demo number 2. This is actually a different curve because it's randomly generated. It might look the same, but it's different. Now this is what I'm going to do. I still have those 30 points, okay, but then 5 of them are missing. So I'm going to transmit those 30 points, 30 green points, over the communication channels, okay? But then randomly, I missed 5 guys, okay? So they got lost, or they got corrupted somehow during the transmission, okay? The question is, can I still recover the blue curves, even when I miss those red dots? So this is the problem called robustness, right? Okay? You can have a very good sampling scheme, but if it's not robust to noise or corruption, we still have a lot of problem, because that means that we have to protect these dots to death, right? So in this case, it turns out that the MSE is still 0, and the curve is perfectly recovered. No error still. Okay? So I can miss 5 out of 30 without any problem. And those 5 missing guys, it can be anywhere. It doesn't have to be any fixed samples. Okay? Next, I want to show you the robustness in a different kind. Okay? So same example. I received those are my measurements. Now, this is what's going on when I transmit this over the communication channels. The true values that I do sampling is in red. Okay? The one that the decoder received is in blue. The one that the decoder received is in blue. So there's error. There's error here, error here, error here, error here, error here. Sometimes I make a large error, sometimes I make little error, sometimes it's exact. But it's random. It's all random. It's all corrupted by a little bit. Okay? The question is, what do I recover from the blue points? Not the red one, from the blue points. We know that from the red one we get perfect. Okay? But from the blue one, what do I get? It turns out that, something very similar, but the MSE is not 0 anymore. There's something. So how different? Very small difference. Very small difference. You see, there's a few things that I miss, say, for example, there, but very, 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 very small difference. Okay? And in the frequency domain, the location of the cosine, I never miss. I never miss the location. I miss the amplitude by a little bit. I miss the amplitude by a little bit. So I come up with something very, very close, but not exact. But for most practical purposes, it's good enough. Okay? So that's the robustness of compressed sensing. So compressed sensing say not only can you sample with very few points, you can actually afford to make errors in those points during the transmission. You can lose some of them, you can corrupt some of them, it's okay. It's pretty robust with respect to noise. So it's a joint source and versus channel coding. You do everything together and the sensing becomes extremely simple. There's no need to do Huffman coding, there's no need to do arithmetic coding, there's no need to quantize, there's no need to do anything. You collect the data and then you just send it over the network, and some of them make it, some of them do not make it, it's okay. Okay, if I receive enough data, I will be able to recover my signal. Okay, so that's the promise of compressed sensing. Now, the next question you have for me would be, fine, you demonstrate a problem on a fake signals, right? That you randomly generated. It's not a real signal. What happens when you take it to something real, something okay? And do you fail or are you gonna be okay? So let me try to show you another example, and maybe let's demonstrate on something that we play around with before. Okay? So now this is a LANA image. Okay? This is my measurement. Okay? So the number of measurements that I make is smaller than the size of LANA. And these guys are not pixels. Okay? They are random. So I do a random projection, meaning that I generate a random noise and I do the product of LANA with that random sequence. I get one number here. And I do it multiple times and I get all these measurements here. So it looks like noise, right? This is going to be what you transmitted over the communication channels. You don't transmit LANA, you transmit this. And then at the decoder, what if I receive this? Can I recover LANA? Okay? So that's the questions. Now, let me run. So now, we're going to have to wait because this is, we're talking about a problem with 512 times 512. This is 250,000 variables, okay? And the computer has to work very hard to try to recover this image. So hopefully, we're going to get it in a few seconds. And we see how robust it is with respect to... So this is a real signal, okay? It's not something fake that I generate. Okay? So that's what I got from those noisy observations that I showed you a while ago. Now, so this is a paradigm shift, okay? Remember in video coding and in image coding, we spend most of our time at the encoder, right? We analyze the signal to death. We try to find the patterns in the signals, okay? And what I'm showing you is the reverse problem.